Hello everybody, today we're going to do a follow-up video to last video we did on ABI encoding. So right now, please go watch that if you haven't. That is step one. Assuming you have, you should now really be an expert on ABI encoding, how to decode a call data, and how to even construct call data. But in this video today, we're going to construct call data by hand, and I'm going to show you how to call a contract with this call data you've constructed by hand. So this means you can call any contract on the blockchain with any call data you want. And I'm going to show you how to construct the call data, of course, so you're calling the right functions with the right arguments. And we're going to go into dynamic types, etc., like that. So consider this kind of like a workshop addition to the other video, which was purely a whiteboard class, if you will. So please subscribe to this channel and give it a follow. If you like the content, I'm going to produce a lot more content like this. So let's get really, really good at ABI encoding today. So to do this, I have created a contract here called ABI Encode by hand. It has an event called results that just emits a number, a uint256. It has two functions, in get and large get. Get just takes an input, a uint, and it just doubles that input and it emits the result with that number. I also have a function called large get. Large because it has more input parameters and also because they're more complex. It takes in an array of bytes. So again, remember from last video, this is a dynamic array. So it's a dynamic type and it contains dynamic elements. Bytes is a dynamic element. This sits in the call data. So the location of this incoming data will be in call data. That just means it's read-only. You could also put it in memory, which means what you would do if you want to write to that incoming data as well. In this case, we're just reading from it, so it's more gas efficient to do call data. Then there's a uint32, which is a static type, as you remember, and there's a dynamic list of uint. So there's a dynamic type, which is the dynamic list, of static types, which is the uints. And this also sits in call data, and so on. This function doesn't do anything meaningful. Like this is just a silly example. But we have this total, which is a uint, and we're just tallying it up. So we're looping over the elements in B, and we're taking their hash. Don't ask me why. That's just what we do. And then we take the uint of that, and we just add it to total. So of course, as you can think, these will be big values, right? Because you hash something, it becomes big. We could mod this to make it smaller, but we have none of that. And then we just add on C, and we add on the element from D, and that's it. We emit the result with total. Why did I do it like that? Well, I just wanted to include something from each parameter so we can see that it actually works and it actually makes sense what we're sending in, instead of just having it rely on something random or no one of the parameters, of course, right? We want to double check that it's actually correct. So that's why. Now what we're going to do is deploy this smart contract on chain, on Sepolia, on the testnet. So not even in the VM here in Remix. We're going to do it on the actual testnet. We're not going to verify it. So it's just going to sit there. And that's just to kind of just kind of even more enforce the fact that this is just some contract that lives there. We haven't even verified it or anything. Of course, we know the ABI. It's right here. But anyway, so we're going to do that now. And then we're going to jump over into Miro, our usual whiteboard tool. We're going to start constructing some call data. All right, so let me first deploy this. So I'm on Sepolia on my account, and I'm just going to click deploy, and that's it. It says pending. Great. So that is being created. Now, in the meantime, what we're going to do is we're going to eventually call this get. All right, so let me actually what we can do is take a screenshot of this. All right. Just gonna create the contract. Yep, there you go. We'll just go over here while that happens. And then what we're going to do is we're going to start constructing the call data for get. All right. So how do we do that? So we learned that last time. So the way you want to do that is you want the method ID, like the function selector of get first. Remember that the first 4 bytes of that function signature, of that function selector, of the hash of that function signature, the first 4 bytes is the function selector. That's what I want to see. And that's what we need to put first. After that, we need to put, and we can kind of do this probably in chunks of 32 bytes when we put the call data together. Remember that from last time, it's kind of everything just works in chunks of 32 bytes. So it's an easy way to visualize it, I think. So the first question is, how do we get the function selector of that function with this signature? Well, there we can go to here. It's a Ketcheck 256 online tool. As an input, we put get, and we put this uint input. Now, we could do it like that. Remember, it has a uint a, but that's actually incorrect. And I want to show you how you can kind of figure out what to put here for the type. You might think it should be uint, but I want to show you over in the documentation as well that when you go under the type here, so you go under uint right here. So that's the type, right? And they list all the types here. Uint is one type, okay? They're saying this is synonymous with uint 256. Okay, fine. So when I write uint, I actually mean uint 256. Okay, fine. But what they're also saying is for computing the function selector, which is what we're in the process of doing, uint 256 and int 256, if it's an int, have to be used. So you can't just use uint. So you can check that the same thing for all the other types if you're in doubt. But my point is that we need to put this, and you see how it changes. Uses the hash below. Of course it does, because the hash of anything, just a small character change, always changes the hash by a lot. So this is very different than this. So now we have the function signature down here. We're going to take the first 4 bytes. One hex character is half a byte. So 1, 2, that's 1 byte. 2 bytes, 3 bytes, 4 bytes. That's it. I'm going to copy that, and we're going to put that over here. So let's make that bigger. All right, so now we're going to prepend the OX to indicate it's hex data. Now that is the function selector. So this is get. This is get with a uint 256 as input. All right. Now we're going to do the rest of the call data. So remember, the call data for a function call is a tuple. It's a tuple of n elements, n being the number of arguments. Here it's 1. So it's a tuple of 1 element. We're going to construct the head. There's only going to be 1 head and 1 tail. All right, of this argument list. Now this is a static parameter. A, it's a uint, that's static, so there's going to be no tail. We know that already. There you go. So we're just going to need the head. The head is the encoding of the value itself. Okay, so let's say that we're going to call it with the value 4. Now, what is the encoding of 4? Like of a uint 256? Well, that is the left padding. Remember that? We got to left pad it with zeros. In other words, we're going to right adjust the value. You do that by left padding it. So the way to do that is, and I'm going to start a new session here. The way to do that is to say, I am going to take the value 4, and I'm going to right justify it. In other words, left padded. And I'm going to do that up to 64 bytes, and I'm going to fill with 0. All right, 64 characters rather. Okay, so that's 32 bytes. So that's what this is. Whoops. That's what this is. All right. So this is 4 encoded, to the call data. So there's 32 bytes. So that's what the head is, and that's what I'm going to put right here. Okay, that's it. That's how to do it. So we did it with the tuples, with the head and tail. There's no tail for a static type, and we took the head, and that is just the encoding of the value itself. And the encoding is the right justification, or in other words, the left padding of zeros. And we could use Python to do that, or any other program. Doesn't really matter. But the point is, this is how to actually call it. So we're going to go back to Remix now, and we can see that this has actually been deployed. We're going to view that on either scan here. Note that this is a poly testnet. That's fine. Note that this is the contract that's been created. You saw that. We can see the events. There are no events yet, but this is where events will pop up. Remember, we're emitting these results as events. So this is the contract we want. So we're going to go back here, and we're going to store that just so we have it. And we're going to go here, and we're going to say 2. Okay, this is our 2 fields in our transactions. This is where we need to put in MetaMask. But that's the contract we want to interact with. Now what we're going to do is, and we just did this by hand, right? We want to call this contract with this hex data right here. The first thing you need to do to be able to do that, we're just going to use MetaMask to do it. You can use other tools like Web3.py, Ether's the JS. There are a lot of other ways you could do this. I think even in Remix, you can do that as well, of course. You can just say this contract lives at this address and you want to send it. I just want to show you how to do it with MetaMask because that's just what I picked. But you need to go into MetaMask under Settings, under Advanced, and activate Hex Data. All right, so what I mean is you go to your MetaMask, and then you go under Settings. Here, you go under Advanced, you scroll down, and you need to enable Hex Data. That is how you can send hex data to contracts. Great. So now what we're going to do is we're going to send something. And actually what we're going to do is expand this view, because I'm going to open up a new tab with this, because or else it'll go away. So I'm going to send to this address. Okay, so send to this address. Okay. And notice this hex data field shows up. We're not going to send any value, any amount. We don't need to. Okay. And I'm going to send this data. What is this data? Again, this is calling the get function with 4 as input. So we expect an event to be emitted when calling this, and the event should have the argument 8 in it. All right. That's what we expect. So we're going to put this call data. So again, this is call data constructed by hand that we're now putting in MetaMask. So we're not going on either scan, under contract, under write. First of all, because it's not verified, so we can't. But we're not showing up on the website. We're just doing this raw. We're just sending raw hex data to that contract. I just want to show you that you can totally do that, and you should be able to do that. So now click next, and we're going to send that data there. So this will all be pending here. And once that, we could speed it up, we're not going to do that. But once that comes through, then we're going to take a look at the events. Okay, great. So that went through, and we're going to go back to this contract on either scan. We're going to go under events, and we're going to refresh this. There you go. So 15 seconds ago, we called get. So we just did that from MetaMask. Notice that either scan actually looks up in a database, right, and finds out that that the function selector actually matches a function named get. It's just so popular, I guess, that it's in the database. Okay, there is a database you can go to. Like you can go from like the function selector to the name. There's a site that does that for you. Okay, but anyway, the point is, an event was emitted from calling this get that we just did by hand. I'm just emphasizing that because that is the whole point. And the argument is 8. That's what was the argument in that event. So indeed, it doubled the value 4 that we sent in. So that worked. Great. Now what we're going to do is, we can go back here. Now what we're going to do is create much more complicated call data, because we're going to create the call data for large get. All right. This stays the same. The to address stays the same. This is now kind of outdated, but we need to get the function selector for large get. Cool. So how do we do that? Notice that it's a bytes array. So what we're going to do is I'm showing you how to do this in general. So that's a bytes array. That doesn't really change. So what we need to do is, again, get the function selector for this. Now, when you get the function selector for something like this, notice that, again, just like always, the variable names don't matter, of course, for the function selector. That would be very confusing. But also, the data location of this incoming data does not matter either. We don't care if you put it in call data or in memory. Doesn't matter. So just be careful with that. So what we're going to do is we're going to do large get of bytes. We have this bytes array first. Again, remember, no spaces between these parameters, and we're not doing things like call data and things like that. The other thing was a uint32, and then the last thing was a uint array. Now, again, you can fall into this trap of using uint, but remember, it's uint256, right? So this is the function selector for that. So that's 1 byte, 2 bytes, 3 bytes, and 4 bytes, and that is the function selector this time. So we're going to do that, and that is how to call large get. Now we need the input for large get. And this time, I'm really going to emphasize breaking it into these 32-byte chunks, because it's going to get very confusing if we don't. Now, remember, we have a tuple now of 3 arguments. So we need 3 heads. There will be 3 heads. I know that this right here, 1, 2, 3, 4. I know that this right here is 32 bytes. So we're going to construct each head. I know that there'll be 3 heads for sure. All right, so actually let me draw that out first. I know that there'll be head 1, head 2, head 3. Let's also say there'll be tail 1, tail 2, and tail 3. This is in general. We know that the second argument, the argument number 2 here, is a static type, so there won't be a tail for that. So we can delete that tail from the list. The head of 1 is a dynamic array. So that'll just be an indication of where that starts. And that needs to jump over all the heads and all the tails of any prior element. Since there are no prior elements, it is the first element. We just need to jump over the heads. Since I have 3 heads, that means I need to put a 60 here, an OX60. Okay, OX60 is 32 bytes 3 times. Okay, so again, that's 96 bytes, but that's OX60 bytes I need to jump by. So again, 20, 40, 60, and then it starts after this one. So it starts in the 4th 32 byte slot, right? So I know that already. Head 2 is just the encoding of the data itself. So let's say we call it, what did we call it with before? Was it a 4? I don't know. We can just say it is. So let's say, actually, we need to define what we call it with. All right. So let's just pick some values. So we're going to say OX11. Okay. We're going to say 4. We're going to say, let's say, like 6 and 8. Okay. And I think, didn't we do that over here? Okay, maybe we didn't. All right. So that's the input parameters. All right. That's fine. So again, the way you do an array of bytes is like, well, you do your array, and then each element of that array is a bytes type. And the way you can write that in Remix, at least, the way it takes that is kind of with these double quotes and then OX, your bytes, do unassent. Okay, so this is what we'll eventually call in Remix, because we're going to do double check in Remix after. The point is, these are the inputs we're going to send in here. So let's say C is 4. That means we're going to put a 4 here. There's already a 4, of course, right here. Great, so we're happy. The last head is going to point to where that starts. It's going to jump over all the heads, which is OX60, but it's also going to jump over the tail of the first element of this guy, aka the tail of this guy. I don't know right now how long that tail will be. I mean, I do. It's pretty easy to compute just based on what this input is. But I'm going to wait. I find it a little bit easier just to wait. It's fine to the end, and then we can just compute it at the end. So for now, we're going to put some question marks here because I don't know the tail. So let's just get started on constructing the tail. The tail for the first argument, and I'm going to leave a little bit of vertical space here so you can say that these are the first 3 heads, right, of the parameter list. Now I'm going to get started on the tail of the first parameter, which is the tail of a dynamic array. What is the tail of a dynamic array? It is the number of elements in that array, which is 1 element. Okay? And then it's the encoding of a tuple of all its elements that follows. So what follows is the head of element 1 and tail of element 1. Okay? Now, the type of what that dynamic array holds is bytes, which is dynamic. So there will be a tail. The head needs to tell us where the tail starts, right? Just like always. And the head needs to tell us where it starts from where the encoding starts. So it's a relative location. So what I mean by that is that this should be a 20. A 20, OX20. It needs to jump over this head, right? That's where it starts. It needs to skip over all the heads, including itself. Remember, just like up here, you always need to skip over all the heads. That's why we had a 60 up here. It skipped over itself, too. It's the same here. This is a 20. It's not an absolute location from the start of all of the data. It's a relative location of the start of where the encoding happened, where this tuple started to happen. So it skips over itself. There's only 1 head, so that's 20. Great, now we've dealt with that. Now we need to put the tail of that dynamic type, which is bytes. Now, the tail will then be the same as the encoding of x being the bytes, this specific bytes right here. How do you encode bytes? All right, and if you're in doubt, you can go look at the docs. The way you encode bytes is you put the length of the bytes here. So in this case, the length is 1. Okay, we have 2 hex characters, that's 1 byte. And then followed by the bytes themselves. But you need to left justify them, aka right pad them with zeros. That's the difference between, units and bytes. Remember that. So here we're going to put a 1. Let's do it with 2 so we can distinguish the data. Actually, we can just do 2, 3, okay? Because that'll help you distinguish the data. So 2, 3, like that. Okay, or else it's just going to be 3 1s. So 2 and 3, that's fine. That's the input. So this took up 1 byte, which is 2, 3. And we need to right pad that with zeros until it's 32. So this whole thing here is the dynamic array of one element, okay, that is of type bytes. So again, 60 is where the tail starts of the dynamic array. 1 is how many elements are in the dynamic array. The rest is then the encoding of each of the elements in the array. In this case, we only have one element, but that element is dynamic, so that has a head and a tail itself. The head is the relative location of where its tail starts, which is just after this block here. Like it's just there's only one head ever in that tuple. So 20 jumps over here. And then we put the tail of the bytes. The tail of the bytes is equal to the encoding of the bytes. The encoding of the bytes is the length of the bytes, 1 byte, and then followed by the bytes themselves. And we're going to confirm that here. So I just want to show you where you could have figured this out. You would go in here and you would say, first of all, as we just said, the dynamic array, as I said, you need to, the way you encode that is you encode the length of it, and you encode then a tuple of its elements. Now again, it only had one element, but that element was a byte. So how do you do a bytes encoding? You encode it with k, the number of bytes, and then you padded right with 0. So pad right means put zeros to the right. Okay, so that's what we have here. All right, so I hope you got that. So that's what you learned in the last video. We did all the heads and tails. We did all the relative encodings, things like that. All right. Great, now we're done with that. So now we can actually kind of go back to the head of the third element, and where does this need to point? Well, it needs to point after all of this has happened. So 20, 40, 60, 80, A, C, E. Okay, that's how you count in a hex, right? So you need to put E0. Okay? You could have also just figured that out by using like a helper tool like Python, things like that to figure out how many. You could count out how many blocks I have. 1, 2, 3, 4, 5, 6, 7 blocks, and then just each of those are 32. Represent that in hex, you would get E0, right? Anyway, the point is now I know this. So this, again, is jumping over all the heads plus the tail of all the elements before me. There's only one element before me, which is that first element, first argument. Great. Now, how do you how do you ABI encode a dynamic array of uints? Well, in the tail of this argument up here is going to be that encoding of the dynamic array. Well, how do you do that? You encode a dynamic array by telling me the number of elements in that array. So what we're going to do is there are 2 elements, right? 2 elements. And then the rest of the encoding is the coding of those elements, but those are static. So technically, yes, we also need to do head 1, head 2, tail 1, tail 2, because you're encoding the tuple of the elements of that dynamic array. Since both elements are static, there are no tails. The head of a static element is just the element itself, but of course, left padded with zeros. So the elements are going to be 6, the elements are going to be 8. Oops. That's it. All right. That's it. That's how to ABI encode this complicated call data. There's a nested dynamic type here. There's a static type. There's just a dynamic type of static types. And this is how to call it from Remix. And this is the call data. We just constructed by hand. So we're going to test this out now. So I'm going to take this right here, and now we just need to start appending this. So this is a little bit tedious, but we just need to start appending this to. Actually, we can take that whole thing and just append that to this. Yep. And just make sure we put like characters in there. There you go. So 2, 6, and then 8. Great. So that's the encoding of that. And I just want to confirm that's just one long byte string. Yep. It looks like it. Great. So that's how it looks. So that looks a little complicated when we put it all together like that. That's why typically also when we decode, we put everything in 32 byte chunks because it makes it a little bit easier to read. Anyway, this is a call to this function large get with these input parameters here. So we're going to try that now. We're going to go to MetaMask. Well, first we need the to address. We're going to go to MetaMask. We're going to send to this address. And we're going to use the hex data that is this. There you go. We're going to send it. There you go. And it's going to be pending now. So yeah, so that's pretty complicated data we're sending. Of course, we were recursively applying the encoding, especially when we had a dynamic array of a dynamic type. We had to recursively apply that, remember? But it doesn't really get much more complicated than this. Of course, you can have infinitely nested types. You can have a dynamic array of a dynamic array of a dynamic array of a dynamic array of a bytes, and so on, right? You can have structs, which are just tuples, things like that. But you just apply the exact same rules. I mean, it's a lot of bookkeeping for sure. So I'm not saying it's like easy, but I'm just saying that there's no new rules you need to know. Great. We just sent that. That just went through. So we're going to go back here, and this is our events. So let's refresh this, and let's see what happens. Great. So we actually were able to call this. Look at this. First of all, this time it didn't find a matching name for this function selector. Remember before it said, oh, I recognize this. This is a function called get that takes you into 56. This time it didn't, because there's no one that's making function names as foolish as me. So there is literally no function name that's called large get. So my brain is pretty orthogonal to these other folks out there with much better names. But the result was emitted, which is great, and this is the value of it in hex, and we can also get it in a number, in a decimal. Actually, no, we need to convert that in Python probably, so we can do this, OX, and then put the number, that's a hex, and then that's going to be something 782 with like 264 at the end, a very large number. We can use that to confirm that what we did was correct. So great. So what we're going to do now is actually try this from Remix itself. We're going to go to Remix. We're going to have this function here. This is deployed to Zipolium, and we're going to call it with the same inputs. So what was it again? It was 23. So this was OX23. This was 4. And this was 6 and 8. So actually what we can do as well is probably just deploy this on Shanghai so we don't spend any gas on that, you know. So anyway, so OX23, 4, 6, and 8, right? Transact, and we can see the result. So we get this number here. So you see this number is something 782, something 264 right here, which matches this number right here. So 7820634, 7820634, and so on. So you can confirm that that's exactly the same, but it is. So that was right. That was the right way to construct this call data, even though it was pretty advanced, right? It was a bytes array and so on. So that's how you do it. It's as simple as that. It's just the tuples, it's the heads, it's the tails, and just recursively applying that. And that's it. So I hope that, you took something away from this video. I showed you how to, first of all, deploy the contract on testnet. I showed you how to construct call data by hand, simple call data and complex call data. I showed you how to take that call data and call a smart contract on chain with MetaMask, and basically kind of refresh some of the rules here. So it's very important that you can do this by hand. It's going to make you a much better developer and an expert in Solidity and Ethereum. So please take some time to practice this and rewatch if you need it. Please feel free to follow and like this video. I always enjoy making these videos and educational content, so thanks for watching. Take care.